Alright, I want to correct the previous errors in the proof of the chain rule from lecture 2. And so here's the chain rule again, but with a correct proof. And I'll just try to rapidly get us up to where the error was last time, and then look into how to repair that. So this is the same setup for the chain rule, same setup as last time. F differentiable at x, g differentiable at f of x. And you can pause the video if you need to reread that stuff. And then the conclusion is then the composite is differentiable at x, and the derivative at x is the composite of the derivatives. So the derivative of g at f of x composed with the derivative of f at x. Okay, so let's get started with the proof again. So since f is differentiable at x, there is some r, some function r, which does the following. It's defined on some neighborhood of 0, and it operates as a remainder for the values of f near x, like this. So you can think of r as being defined by this equation, and what makes f, I mean, you could always define r by this equation, but what makes f differentiable, sorry, this should say r of h, not r of x. What makes f differentiable at x is that this is true, that r of h over norm h limits to 0. And similarly, since g is differentiable at f of x, there is some s defined on a neighborhood of 0, such that g of f of x plus, and then here's one of my mistakes last time, is I wrote h here, and it's not really a mistake, it's okay to write h, but it's just not the same as the h here. So that really got things muddled, I think, and led to some of the confusion. So I'm going to use a different letter, k. So g fx plus k is going to be g fx plus g prime fx applied to k plus s of k. Alright, so, oh yeah, and also the limit as k goes to 0 of sk over norm k is 0. So these are the two facts, the same ones I stated last time. And I'm going to try to use these to show that g composed with f is differentiable at x. And I guess to really complete the sentence here I should say for all h in the domain of R. And here I should say for all k in the domain of S. Alright, so proceeding just like last time, I'm going to start with g composed with f of x plus h, and see what I can do with that. See if I can get it to look like a linear approximation plus a remainder, and then see if I can show that the remainder goes to 0 fast enough. So this is g of f of x plus h, and then f of x plus h from up here is f of x plus f prime xh plus r of h. So, and now I've got g of f of x plus some displacement, some k here. So this will play the role of k. So this would be g fx plus g prime fx of k, which is this underlined yellow thing, f prime x applied to h plus r of h, plus s of k, and this is the mistake I made last time. It should be s of this yellow thing. For some reason, I just didn't do it that way. All right. So then we almost are where we need to be. So this, let me write it using composition. This first this is linear, so it distributes over this sum. And so the first term I get is the composite of these two linear maps, which is what I'm trying to get out of the chain rule, basically, applied to h, plus, and then the remainder stuff is g prime fx of r of h plus s of f prime x h plus r of h. Now, we will be finished, just like in our work last time, we will be finished if we can show that this thing goes to 0 fast enough, this remainder. Then we have exactly what we need. So call this t of h. Then what we need is that the limit as h goes to 0 of t of h over norm h be 0. And last time this was much easier because I made a mistake, because I had this term correct, and then here I had s of h. Now it's going to be a little bit more complicated. So if I look at t of h over norm h, that's g prime fx of rh over norm h plus this other thing over norm h. So we are trying to show that this thing limits to 0. So just like last time, this causes no problems because it's bounded above by, so in norm, so let me stick some extra norm bars here, and let me use the triangle inequality here so I can stick norm bars here and here individually on these terms. Then this thing is bounded above in norm. This thing is bounded above by the norm of this linear map times RH over H. And we already know that this thing limits to 0 as H goes to 0, right? So there's no problem there. So this term causes no problems. What's left, now what we need to finish the proof of the chain rule, is we need this remaining part to limit to 0. The second term there. That's what we need. Okay, so now we're just this one step away from finishing. And this is more complicated than it was when I was doing the proof incorrectly last time. So I don't know if there's a really very good way to avoid getting our hands dirty with epsilons and deltas for this one. So, I mean, somehow we have to use the fact that sk over k goes to 0 as k goes to 0. So let's just do it with epsilons and deltas. So first of all, this statement about s tells me that if I manage to make if I manage to make this thing here small enough, then I will know that this is smaller than or equal to, well, then I'll know I can make this thing small. And not just smaller than epsilon, but smaller than epsilon times the norm of the inside thing. Okay, let me just show you what I mean. So let epsilon be greater than 0 for the sake of trying to prove this limit statement right here. Then due to this limit statement here that we have, there is some delta, let's call it delta 1, such that whenever k is less than delta 1 in norm, we have the norm of sk is less than epsilon times the norm of k. So that's using this limit statement here. And actually, I don't need to put epsilon here. I can put any positive number I want. So the epsilon I fixed at the beginning, that's the epsilon that I'm going to use for the sake of proving this limit statement here. But I can use any positive number I want down there. So let me call it epsilon prime, and then let me pause the recording, do some scratch work, and figure out what epsilon prime needs to be. So I'll be right back. Okay, I'm back, and this is the epsilon prime that I think works. And you don't have to believe me yet. The point of the proof is to show that it works. But hopefully you believe that any positive number I pick here, for any positive number I pick here, there's a delta 1 that makes this work. All right. So now, if I make h small enough, so I will be able to make use of this this delta 1 if I can ensure that whatever is here is being stuffed into the s is smaller in norm than delta 1. So how can I do that? Well, this thing, if you plug in h equals 0 into this thing here, you just get 0, right? And in fact, this thing is continuous at h equals 0. So let's make that point. So the mapping h goes to f prime x of h plus r of h is continuous at h equals 0. This is a function that's defined on whatever is the domain of R, and it sends 0 to 0. And we have seen before that R is continuous at 0. That fact follows from this limit statement. So we've seen before how this tells us that the R must be continuous at 0. And, just looking at, this information together here tells you R is continuous at 0 and takes the value 0 at 0. Okay, so this mapping down here is continuous at 0. So that means there is some delta 2. Greater than 0, such that whenever h, actually this is a continuity, not limit that I'm using, so whenever h in norm is less than delta 2, we have that the norm of that thing is less than, and then I can put any positive number I want here. So I'm going to choose delta 1 as my positive number. Okay, so that's looking pretty good. Let's see where that gets us. So maybe this delta, remember the goal was to prove the limit statement over here. This was our goal. So maybe that delta is a sufficient response to this epsilon in order to prove this limit statement over here. So let's try. So let me just say let h be such that h is not 0 and is less than the delta 2 there. I'm not saying what domain, where h lives exactly. So it's an n tuple, so it's some vector in Rn, but it needs to both be in the domain of R, and it needs to be such that this quantity here is in the domain of S. And we've discussed before what kinds of h's would satisfy that, and I rambled for a little while about why it would be an open set, a neighborhood of 0 worth of h's. Let me not get into that detail so much. So let h be such that this is true, and how about, to skip that detail, I'll just say and such that this thing inside of S is defined. So there is an open set's worth of such h's. Then, due to the choice of delta 2, this is true. This is less than delta 1. And then due to the choice of delta 1, when you apply S to this thing, sorry about the handwriting there. When you apply S to this thing, you get something that's less than epsilon prime. So what I'm following right now is this fact about delta 1, that it achieves this. And I've got that big expression playing the role of k. So here epsilon prime times the norm of that big expression. Alright, so I haven't quite succeeded yet, because what I want in the end, so let me go back to what we're trying to do. We're trying to prove this thing in the red box, right? So what I want in the end is that the norm of S of that big expression is less than or equal to epsilon times the norm of h. So my hope is that after a bunch of talking here, I'll get that this is less than epsilon times the norm of h. So that's where I hope to get to. Okay, well, it is less than or equal to, by the triangle inequality, this. Which is less than or equal to, using the definition of the norm of this linear map, this, times h. So there's an h coming out, and that's really nice. And Now, how do I control the norm of this RH? Well, I think to do that, I think right now I have not successfully controlled it, but I can control it. So my goal to get this to work is to get, I want an H to pull out overall here, right? So if I want to control the norm of this RH, what I want to do is get it to be less than some number times H, times the norm of H. And I should be able to do that thanks to this statement here, this fact about R of H. So I can always get, by making H small enough, I can always get R of H to be smaller than any positive number I want times the norm of H. So going back here, or going up rather, I should insert something in here. So before I decided that I have my delta that I need, I should insert something. So let me move some things around and I'll be right back. Actually, it probably helps for me to show you what I'm moving around exactly. So let me do that. So this is our proof at the moment. Let epsilon be greater than 0. Then we got our delta 1. That makes this thing work. And then we got our delta 2 using our continuity of that big expression there. Then I want to get a delta 3 before I go acting like the delta 2 that I got was sufficient for finishing the proof. So here I'll say, or actually, yeah, let me do it in a different color. There is some delta 3 greater than 0, so that whenever H is less than delta 3 away from 0, we have R of H, norm, is less than, and then I can put any positive number I want times norm H. And the positive number I pick is 1. I think that should work. And now over here, where I fix H, instead of using delta 2, I'll use the minimum of delta 2 and delta 3. All right, so now all this stuff still works like before. However, I can now go here and say this is less than plus H, norm H. So I've got norm RH is less than norm H. Okay, now I can pull out the H. So this is epsilon prime. And now you can see why I chose epsilon prime the way I did. In fact, I don't think I needed to choose it quite that way. I guess it would have been enough back here to say epsilon prime is just epsilon times this thing. Then here I get epsilon H. Okay, so there's the corrected proof of the chain rule. And I'm kind of glad that I'm glad that the approach I ended up going with required at an epsilon delta proof, because it's an analysis class, right? I think we haven't done a single epsilon delta proof, and that's like the main thing we should be doing, right? Yeah, and I guess it also makes your virtual lecture experience more authentic to how real lectures are, which is full of errors.